Welcome. To determine if a sequence is convergent or divergent, ask one simple question. As n approaches infinity, do the terms settle toward a single fixed number? A sequence is just a list of numbers following a rule. We denote them as a sub n. If the answer is yes, it's convergent. If the terms grow without bound, jump around, or never settle, it's divergent. Convergent sequences approach a finite limit. Divergent sequences move away or oscillate indefinitely. Remember, convergence is all about finding stability. To classify sequences instantly, we use the COD memory trick. C stands for close. If the sequence terms approach a single finite number, the sequence is convergent. O stands for oscillates. If the terms bounce back and forth between values without settling, it is divergent. D stands for drifts. If the values grow or shrink without bound towards positive or negative infinity, it is divergent. Remember, only sequences that drift close to a finite limit are convergent. Oscillating or drifting sequences are always divergent. The plug-in heuristic is a simple, powerful tool for your mathematical toolkit. When you want a quick sense of whether a sequence converges, simply plug in very large values for n. Let's look at this sequence. As n grows larger, notice how the result gets closer and closer to 2. This suggests our limit is 2. If the numbers settle, it's likely convergent. If they keep growing or changing wildly, it is divergent. Remember, this is a heuristic, not a formal proof, but it is excellent for rapid verification. Recognizing patterns is the secret to solving limits quickly. First, look at reciprocal powers like 1 over n. As n grows, these terms shrink, always approaching 0. For rational functions, ignore the small constants. Just look at the ratio of the leading coefficients. In 5n plus 1 over 2n minus 3, the constants become irrelevant. The limit is simply 5 over 2. Keep these two takeaways in mind. Reciprocals always head to 0, and rational functions are defined by the ratio of their leading coefficients. Spotting these patterns makes solving limits much faster. Using digital tools like Desmos or GeoGebra can transform your understanding of limits. By plotting the terms of a sequence, we see how they behave as n increases. Notice how the dots move closer to the value of 1. The horizontal dashed line represents our limit, L equals 1. Modern software allows us to draw a neighborhood around the limit. As n grows, the sequence enters this narrow band and stays there, which we call the tail of the sequence. This visualization helps build computational intuition, letting you see the rate of convergence firsthand. It's an essential step in mastering calculus. The first common trap is confusing boundedness with convergence. A sequence can stay within a fixed range, like -1 to 1, and still fail to converge because it keeps oscillating forever. A classic example is the sine of n. The second major pitfall is confusing sequence limits with series sums. Even if a sequence approaches 0, like 1 over n, the infinite sum of its terms can still grow to infinity. This is the harmonic series trap, where the sequence converges to 0, but the series diverges.